Alright, welcome back. So this is our first video with Unit 7. We've done a couple trig units already with our trig, solving trigs with triangles in Unit 5. Get introduced to the idea of trig expressions and graphing trig functions with Unit 6. Now we're taking a look at our trig identities. And there's numerous different identities we're going to go through. We're also going to talk about how to solve them, and then we're also going to talk about how to do a trig proof. Not the same kind of proof you did in geometry with your statements and reasons and everything else like that, but a similar kind of idea. It's about logic, about rewriting it to make them all the same. We'll get into that. 7.1 is our fundamental identities. So starting off with, we have our quotient identities, governing how tangent and cotangent are relating to sine and cosine, tangent being sine over cosine, cotangent being cosine over sine. Next up, we have our reciprocal identities. So this is now, each trig function has its reciprocal. Sine is reciprocal with cosecant, cosine with secant, tangent with cotangent. So we can always just simply flip it. If I know sine, 1 over that gives me cosecant. If I know secant, 1 over that gives me cosine, and so on. And then we also have our Pythagorean identities, which, so this one right here is a repeat. Sorry, this would say cosine squared is 1 minus sine squared. But they're all based on the Pythagorean identity sine squared plus cosine squared equals 1. Everything else we do comes from that, because if I divide everything by sine squared, I create the cosecant squared and cotangent squared identity. If I divide everything by cosine squared, I create the tangent squared identity. And they're just different ways to rewrite them, but as long as you know this one right here, you really know them all. And what we're going to ultimately really do is we're going to use these three different identities, mainly the Pythagorean identities and the reciprocal, but you can use the quotient as well, to find missing trig functions. Also to help us find these different missing trig functions, we have the quadrant information right here, telling us where things are positive, where things are negative. This is also known as all students take calculus, where all trig functions are positive, sine is positive, tangent is positive, cosine is positive. And remembering, if cosine is positive, it means secant is. If tangent is positive, so is cotangent. And if sine is positive, so is cosecant. Alright, now, the way you're going to want to go about doing this is you're given one function, cosine is negative 3/7, and we're also told another function is positive or negative. And that's going to narrow us down to what quadrant we're in, so we know our final answers are positive versus negative. We'll worry about that. Let's worry about that right now. We'll do that first. So cosine is negative in quadrants 2 and 3. And cotangent is positive in quadrants 1 and 3. So the overlap is quadrant 3, and that's what we're operating in. Now, we're given cosine, and we want to find sine and secant. So what I always find useful is I'm starting with cosine. Cosine can get to sine with our Pythagorean identity, and it can get to secant with our reciprocal identity. So we can see that's what we want, so that's how I'm going to follow my pattern there. So I'm going to flip first. That's easy. Secant would just be a negative 7/3, nothing too fancy there. And then sine squared, we know is 1 minus cosine squared, so it's 1 minus 3/7. So the 3/7 squared is 9/49. So I'm going to rewrite the 1 as 49 over 49. So I have that common denominator. Sine squared is then 40 over 49. And now I'll square root it. So sine would equal, well, the square root of 40 is going to be a 2 root 10. Square root of 49 is 7. And then whether it's positive or negative, because we had to square roots, well, we just saw that when I did my check marks there, I'm in quadrant 3, where sine is negative. And there we go. So if I'm given just your simple Pythagorean and then reciprocal identity problems, that's all I'm looking to do right there. That's it. If I was trying to find something else that needed us to then go past sine or secant, then I have to use other methods as well. So let's kind of take a look at some more interesting ones. So in this scenario, so first off, we'll figure out our quadrant. Cosecant is negative in quadrants 3 and 4, because it's based on sine. Tangent is negative in quadrants 2 and 4. So quadrant 4 is our overlap, and that's what we're operating in. Now, they want us to find sine and cosine. Well, cosecant gives us sine and cotangents, and then sine gives us cosine. So that's the pattern I want to go through. I don't need to use cosecant to get to cotangent. I can use it to get to sine, and then use sine to get to cosine. We certainly could use sine and then cotangent to then get to cosine because it's a quotient identity, but it'll be much quicker to go to sine and then use sine to get cosine. So if cosecant is negative 7 over root 5, sine would just be negative root 5 over 7. And then cosine squared is 1 minus sine squared, so 1 minus negative root 5 over 7 squared. We're going to get a 5 over 49 here, so the 1 is really 49 over 49. Subtracting gives us cosine squared to be 44 over 49, square rooting that. The square root of 49 would be 2 square root of 11, and the square root of 49 is 7. We are in quadrant 4, where cosine is positive, so it's positive 2 root 11 over 7. All right. So again, that little tree I'm doing off to the sides will be very useful to kind of tell us where I want to go, the direction I want. Because really, once I know one function, I know them all. Because I use, like, cosecant tells me sine, and it tells me cotangent. Sine gives us cosine. Cotangent would then technically give us tangents. And then both of those could give us secant based on how you want to go through it. So one tells us everything. It's just a matter of what's the pattern I want to go through. What's the most efficient way to get the 2 trig functions I want if I only are asking 2 trig functions. Or if it only asks for 1, what's the best way to get to just that 1 it wants. Alright, so one more. We got tangent is a negative 3/5. So tangent's negative in quadrants 2 and 4. Sine is negative in quadrants 3 and 4, so we are once again operating in quadrant 4. So they give us tangents. They want to find secant and sine. Well, tangent goes to secant with the Pythagorean. It then goes to cotangent for the reciprocal. Secant goes to cosine. And then cotangent would then go to cosecants, both of which would then go to sine. So it looks like our best bet is to take tangent to get to secant with your Pythagorean, flip secant to get cosine, and then we can either use the quotient identity or another Pythagorean identity to get to the sine value from cosine. Do something a little bit different. I'm going to use Pythagorean to get to secant, flip to get cosine, and then I'm going to use the quotient with tangent and cosine to get sine. So first off, secant squared is 1 plus tangent squared. So our tangent squared would be a 9 over 25. So 1 is really 25 over 25. Which means secant squared is 34 over 25. Square rooting it gives us secant to be root 34 over 5. And it's positive because we are in quadrant 4. I then flip that to get cosine, which is necessary to get to our sine. So it's 5 over root 34. I'm not going to rationalize it because I might need to use it later. I'm going to use it later on, so I'm just kind of leaving it its unrationalized form. Maybe I'll be able to get rid of the radical later on, so let's just kind of see. I know that tangent is sine divided by cosine, which means sine is tangent times cosine. So our tangent value is negative 3/5. Our cosine is 5 over root 34. You'll see the 5's cancel. Sine is a negative 3 over root 34. Negative makes sense. We're in quadrant 4. Sine should be negative. Unfortunately, the radical didn't disappear, and it's still in the denominator, so we have to rationalize now. And we get sine theta to be a negative 3 root 34 over 34. And we would have gotten this exact same answer if we had gone through our Pythagorean identity instead, solving out for using cosine squared equals the 1 minus sine squared to solve it out that way. So it's up to you. More often than not, the quotient identity will not be practical because you need to know 2 of the 3 to be able to really work with it, whereas all the other functions just need one thing. You need to know secant to get cosine because you flip. I need cosine to get sine for the Pythagorean identity. So I need 1 versus just needing to know 2. It just kind of depends on where you're given. All right, so setting up that little tree off to the side can be very helpful to kind of help show you the flow of what is the most efficient pattern to use. Now, a couple other basic trig identities. We have the co-function identity, which is showing us that if we are doing pi over 2 minus theta, we can get to a equivalent function here. That's kind of based on your like functions here. Now, notice it's pi over 2 minus theta, so if it was the other way around, we'd have to rewrite that. And we'd rewrite it in a way that would create a negative angle inside. This would be the same thing as negative of pi over 2 minus theta. And because it's a negative, we now need to talk about the negative angle identities. So, and this one you have to make sure you're careful with. For cosine and secant, the negative inside would just cancel and just go away completely. It's because they are even functions, because they are symmetric about the y-axis. Whereas all the other ones, sine, cosecant, tangent, and cotangent, the negative doesn't cancel, but it pulls in front. Meaning, for example, if I have sine of negative 3x, that's just negative sine of positive 3x. I just pull the negative in front. So, and that's what's going to happen when we have that pi over 2 situation where it's in the wrong order. I factor it away, so then this becomes really the negative sine of pi over 2 minus theta, which means it's negative cosine for that final result. So that's the kind of thing we're going to have to work through on the next couple of examples, applying our negative angle identities and our cofunction identities. So here we're given cosecant is negative theta. We want to find secant of pi over 2 minus theta. So secant of pi over 2 minus theta is in our correct order. It's the pi over 2 first. And that is equal to cosecant theta. So I need to figure out what cosecant theta is. Well, the cosecant of negative theta is equal to negative cosecant of positive theta. The cosecant of negative theta is really 1.29. So cosecant is negative 1.29. And that's what then secant of pi over 2 minus theta is. So we're not going to do anything really crazy with this stuff. It's just simply a matter of figuring out whether the final result is positive or negative. It's all about pulling negatives outside of functions, canceling negatives, setting up equivalent expressions, stuff like that. All right, so we have our last example here. So for this one, we can recognize that we're trying to find cosecant of negative theta. So to do that, since that's equal to cosecant of negative cosecant of theta, we need to know what cosecant theta is. That's where the secant theta minus pi over 2 comes into play, but it is in the wrong order, so we do need to factor the negative away to make the proper order pi over 2 minus theta. Now, with secant, when you factor away the negative, it actually just completely cancels. Secant and cos and the negative is not pulled out in front like it was with cosecant, it just cancels out. So secant of pi over 2 minus theta is just 1.27. And according to our formula, we know that's equal to cosecant theta. So cosecant's 1.27, which means cosecant of negative theta would be a negative 1.27 when we fill in that. So again, there's nothing fancy really going on here. You just have to be careful using your formulas, pulling out the negatives, stuff like that. All right, so those are your basic identities. We're going to use these a lot for the next video when we get into the idea of verifying our trig functions, as well as using them throughout really this section and any other future units involving trig. So don't forget them. The Pythagorean identity for sine squared and cosine squared really shows up very, very often. So you want to make sure you always have that one down. All right, so that's it. And I'll see you guys next time for the 7.2 video.